I'm Luka Jacobowitz, and I'm going to talk to you about reactive programming in the browser in Scala.js, which is a Scala to JavaScript compiler, and Rx, which is basically the reactive extensions, and yeah, we'll get into that soon. So, first up, our agenda, small overview. The first thing I'd like to discuss with you is how can we develop purely functional front-end applications. That's a very difficult question that a lot of people have tried to answer in different ways, and we're going to take a look at that. And then we're going to talk about the title of my talk. So what exactly is reactive programming? What does it mean? And what does it mean in the sense of user interfaces? And then I'd like to talk about the pros and cons of the reactive approach. What are the actual benefits of doing things like this, and then a small live coding session, depending on how much time we have. So, without further ado, how do we develop user interfaces with pure functional programming? This is an especially difficult question because if we look at code in the browser, it's usually riddled with effects or side effects. So if we try to just wrap all of our effects in some kind of IO type like cat's effect or Monix task or FS2 task, SCSI task, whatever, you would get code like this. And can you read this, Ryan? Yes. Yeah, okay, great. So what we can see here is every time we create an element, a DOM element, or we add an event listener, that creates a side effect, right? So even when we query the DOM, like give me this node, that also creates a side effect. So what we do here, in essence, is we have to use our IO monad and just create a sequence of these effects to actually create a program. And as you can see here, this is very messy, and all that this program does is just create a button, and every time you click it, it will just add text to the span beneath it. So this is a lot of messy code for very little gain. So what some people have come up with, not me, but some people have come up with is a different kind of architecture to this whole problem. And that is the following. So let's try again. This time we have a function called app, and it takes an update function, like it's a higher order function, from state to state. Like updating a state is just a function from state to state, and also takes a view function that takes a state and returns some kind of representation for our DOM, which here is called HTML. And what we can see here is then every time we want to change something, we get our current state, we update the state using the update method, update function, and then we render it with our view function. We return it into a DOM representation and render it, and then that's a whole program, right? So every time some event happens, every time we want to update our UI, we have to go through all these steps. And what we can see here, this already decoupled some of it, right? So we have the state updates as part of like one part of our app, and the other part is just dealing with how do we actually display the state in the DOM. And you can see right here that it's just I created some kind of div button span. This is basically just functions that turn something into an HTML representation. This is basically just pseudocode, pseudo Scala. This isn't any actual code, but it's trying to get this idea across. So in the end, then our program is just app of update and view. So we can go even further, because I don't know how many of you here have used something like Redux or Elm. Okay, that's quite a few. So with Redux and Elm, specifically the Elm architecture, have basically pioneered is something where we have a globalized store, and all we do is, instead of writing functions that update state, we just send a small action, and depending on this action, the state will be updated automatically. So what we have here is a sealed trait hierarchy called action. And then all of our actions are just cases of this action type. So here we have an action append text. And what we can then do is pattern match over this action. And then basically what we get is, again, a function from state to state, right? This reducer function takes an action and a state and returns a new state. And this is very useful because instead of having to basically, if you have a very, very big app and you're in basically a leaf component of your app and you want to just update a very, very small thing in your app, you don't have to actually write a function that updates the entire app state. You can just send a small action and then it will take care of it for you. So now our new app function is actually very similar. We again get the current state, we update the state using the reducer, and then we render it again. Okay, so the next question is, how do we query or update the current state, right? So we had these get current state and save state functions that returned some kind of I/O, but how do we actually implement something like this? So the first thing I thought about was how about using something like the state monad, but the state monad only really works when you're inside a specific context, a computation, for example. So this might work if all we did was synchronous, but it's not really great if we want to do async stuff like clicking something 10 minutes later or something like that. So another thing might be mutable references, right? So we have this globalized state somewhere, and we can just add a mutable var somewhere, like at the top level of our code, and just reference that and wrap it in an I/O or a task, and then call it a day. So that would be probably the easiest way to do it. And then what about something like free monads? Free monads could be a good idea to do the same thing. We could basically, in our implementation of the free monad in our interpreter, just use mutable references or something like IORef. The advantage here would be that we could combine this with different side effects you might want to do outside of DOM manipulation, right? So mostly client-side apps usually have some kind of side effects like accessing date, or of course accessing HTTP, making HTTP requests, or WebSockets, things like that, or local storage. So lots of side effects. But the thing I want to talk about is streams. We can query and update current state with streams. And this basically is the heart of reactive programming, especially in the UI sense. So a definition of reactive programming can be, reactive programming is just basic programming with data streams. And usually these strings are asynchronous in nature. So this is a visualization of some kind of example stream. So in reactive programming, we like to think that all of our application can be modeled with these kind of streams. So if you go at a very, very low level and you think about your mouse is just a stream of its position and maybe a click, a mouse wheel, something like that. So we have these streams of XY coordinates, for example, or your keyboard is just a stream of different key inputs, right? So basically, we could take these streams and we can combine them and do stuff with them, and then at the end of our program somewhere, we could return something like a pixel grid, right? That just draws our whole application. So this is at a very, very low level. You could model your program like that. I'm not trying to tell you you should, but this is the kind of mindset you're supposed to be in when you try to understand the whole concept of streams. So what this is basically here, this represents some kind of time, like right now, I know it's 1040 is right here, and then this is 1040 and 1 second, right? So this guy typed hello, and this just represents the time in between here. And for some reason he did it all in all caps, I don't know. So what's cool about this is that streams are functors, and that means we can map over them easily. In this example, we get a new stream where we just lowercase all of the inputs we get. So before we had a stream of hello all in all caps, and now we get a stream of hello in the lowercase. So analogous to the collection library in Scala, every time we map a collection, we get a new type of collection, right? So this is an immutable operation. So, and the cool thing about this, streams are also applicative. So you can combine a lot of streams, you can merge them. There's different strategies to combine different streams, but that's another subject. What I really want to talk to you about is the scan function. Does anyone know the scan function from the Scala standard library, the collection library? A bit. Okay, yeah, one of you. Okay. Yeah, there. Okay, great. So basically, the scan function, I'm just going to show it, is very similar to a fold. But whereas a fold waits for the entire sequence to emit its value, right? So if we fold a list of 1, 2, 3, we get a list of we get a single value of 6. We create intermediate values. So if we scan over a list of 1, 2, 3, we would get a list of intermediate values instead. So we get a list of 1, and then a list of 1 plus 2 is 3, and then we get a list of 1 plus 2 plus 3 is 6. So we get a list of 1, 3, 6. And in observables, this is inherently more useful, because if you want to fold over an observable, which is a stream, I'm sorry, I just threw this new term out there. Observables are streams in Rx. This is its specific. But yes, this is incredibly useful, because if we want to fold over a stream, we can't, because streams can be potentially infinite, right? So a mouse position doesn't really end or something like that. So these streams are potentially infinite. So in order to actually accumulate state, we need something like the scan function that creates intermediate value. So if you run the scan function over this, we get a new observable that just adds, like string concatenates, which sadly is a plus in Scala, these strings. So we get h and then he, hel, hel, and hello. So this is the basic idea of how you can accumulate state in reactive programming. But so far you might ask yourself, okay, so that seems kind of complicated. Why didn't you just use like mutable references? What's the advantage of this? And the cool thing is that streams like kind of abstract away time. So, and I'm going to show you what this means. So how is this useful? This is, for example, the debounce time operator. And what this does is it takes every time a value is emitted in the original stream, it will wait the amount of time, and if there's no value in between the first value emitted, like here, and the end of this time period, then it will just emit the value, right? So here it waits 20 milliseconds, and then whoop, it just emits the new value. Here, B emits, and then it waits, and then it sees, here's a new one. So we're just gonna emit that one at the end of the period, right? So then we go here and nothing else comes, and then we emit C. And then the same as A goes for D. So and how is this useful? Think of, for example, you're trying to create a search functionality in your front-end application. Usually you will want to get search what is it called? I'm sorry. Search result as you type, right? So what this does in essence is it can create these HTTP requests as you type, but it will only do it after your specific amount of time. So every time you create a keystroke, it won't automatically send an HTTP request. It will wait the amount of time, and it will then create the HTTP request with the last result it gets. So this is really useful, because if you try to model this, like think of how to do this imperatively. Like it's really difficult, because you have to deal with these timers, you have to think like, oh, how do I have to reset this timer? Oh God, it's incredibly difficult, and especially if you want to do it in a pure functional way, because the timers are inherently effectful as well. So this basically just abstracts away over this, and it's pure in a sense, right? So this is one really useful operator. Another really useful time-based operator is something like buffer time. And buffer time, you also give it an amount of time in milliseconds, and what it then does is it just buffers all of these items in the specific time period and creates a list out of them. So we can see right here, every 100 milliseconds we're going to create some kind of buffer, and here we buffer together A and B. And then we create the new observable, the new stream emits a list of A and B. And here we have CDE, and here we have FG. So this is really useful if you think of like something where you're just, where you have a lot of interaction with your UI, and you want to create some sort of, maybe like an HTTP request again. And in essence, instead of creating like hundreds of small HTTP requests, you can just create, buffer them together, and then create one HTTP request that will get you all of the data you might want to need based on these interactions. So basically, again, this is a time-based operator that can optimize a lot of things away from you, abstract a lot of things away from you to optimize your code. Okay, so the next thing I'd like to talk to you is about OutWatch. And that is the small library I created to make all of this more or less painless in Scala. So the first thing I'd like to talk about is updating DOM, right? So at the beginning we said we had this HTML representation. We could just write an HTML representation that just recreates the DOM every time. So we have this huge DOM tree, and then we get a state update, and then we have to just render it all again, but that's incredibly expensive. So thankfully, when I wrote OutWatch, there was already tons of libraries implementing something called virtual DOM. And the virtual DOM is a technique where you create, again, a DOM abstraction, but instead of updating the whole thing, it creates a diff between two virtual DOM trees, and then it will only update the small differences. So if you have two virtual DOM trees and they're exactly the same except for one tiny like subcomponent somewhere, it will only update that subcomponent in the real DOM. And that's really useful. And that's what React uses, for example, and that's what makes them a Vue.js. Maybe you've heard of that as well. And that what makes it so performant. And another thing is OutWatch tries to handle subscriptions automatically. Subscriptions, in case you've worked with something like RxJS, RxJava, Rx Scala, or even Monix. Monix is also a streaming library very similar to Rx. Basically, whenever you have an observable and you want to actually do something with it, you have to subscribe to it, and that creates a subscription object that holds on to all of the resources your stream might have. So for example, if you want to create a click listener, an observable that reacts on click events, once you subscribe to it, the subscription will hold on to the registered event listener, right? So once you actually unsubscribe from that subscription object, only then will it actually remove the event listener. And that means that if you forget to do that, you might leak some memory, and it might cause all sorts of problems. So OutWatch tries to do this to just take all those things away from you. If you use OutWatch, you're never really going to see a subscription event, a subscription object. Okay, and another cool thing is that it's completely polyglot. And that means you can use Scala, or you can use something like PureScript if you're really into pure functional programming. You can just choose, there's documentation for both, and I'm trying to push both as much as possible. There's like more or less feature parity. Like there's like maybe one or two small features that like don't work in the other language, but yeah. Okay, so let's check out some code. go. Okay, so this is just the basic, boilerplate, I guess, for creating an OutWatch app. We have this OutWatch.render method, and you can see this, right? Yeah. Sorry, I usually forgot to ask. Okay, so and this just takes a query selector and a function that returns a vnode, right? Actually, it's just a vnode, and a vnode is just a virtual DOM node. And here we can see it just right now it just has an empty div. And what I'd like to do as an example application is just create like a small app where we'll want to do some kind of dynamic lists, because that is so common. And we'll use the Elm architecture for it. OutWatch supports a lot of different architectures, but this is the one I'll choose for now because it's the easiest to showcase. Okay, so first we'll want to create a sealed trait hierarchy called action, where we want to describe all our actions. And the very first action, the very simplest action, is just we're gonna want to create a new item in the list. I'm gonna call it add new item. It's gonna extend action. No. And now another thing we might want to do is update some kind of item. And for that we need an index, type int, and we'll need the updated item. And for now we'll just give it like the type string, because we don't want to write a lot of code right now since it's just a demo. And our state right now is just going to be very, very simple. It's just going to be a list of string. And our initial state, like the beginning, initial state I think speaks for itself. Which is going to be of type state is just going to be list.empty. Okay, so we defined our state and our action types. Now let's just write a short reducer function. That's going to take the old state and the action, and it's going to return a new state. And for that we're going to match on the action. And in case we have a new item, in case we want to add a new item, we're just going to say the old state, which is a list of string. I'm just going to add an empty string for now. And the other case is we want to update. And what we're going to do there is here index and item. And we're just going to take the old, and we're going to use the updated function, which just basically returns a new list updated at the index with the new element. So this is very, very basic, but it should work for now. And now what we need to do is we need to create a view for our list. So the first thing we want to do is create a view for our item. So we'll just call it item view, and we need to parameterize this by the index and the actual item, which is going to be a string. And we want this to be, I guess, just like a list item. And what's in here, what we're going to need is we're actually going to input an input field. And we're just going to add a placeholder really quick. Say, I don't know, enter item. And we're also going to, every time we want to input this, we want to actually update the state, right? So what we're going to do is we're going to use the input string type. And it takes a function from string, because every time we input something into an input string, and then you return a function to your action method, right? So in this case, it's update, and we're going to take our index and our actual s, which is just the string of the text field. So, and now we actually have to bind this to a store that we have not yet created. Oops. Okay, so let's just create a store real quick. And a store is just basically like a Redux store. Takes an initial state and a reducer, and that's it. There we go. Okay, so now we have our item view. Now let's create an item list view. And that's going to take a list of string, which is just our state, and it's going to return a list of vnode. The item view also returns vnode. I just didn't add the type annotation. So what we're going to do right here is we're just going to take the list, and because the list doesn't have, if we want to call map on list, it doesn't have the index, so we're going to have to zip with the index before. And now we have right here, this is this should be a list of a tuple of string int, right? Okay, and now we can map this and just get the, I think this should be the item and the index of each item, and then we can just map it to our item view, index item. And now we have a transformation that takes our state and returns a list of vnode. So now what we can do is just inside our main view function, we'll want to bind this to our store, right? So we can use something from OutWatch called the children binder, and it will take an observable, and our store is also an observable. And it only works if it's a list, if it's an observable of a list of vnode. So we can map our store using the item list view, and this should work. Sure, yeah. Okay. Actually, let's wrap this whole thing in a UL before, because I'm not sure why my computer is so slow right now. Sorry about that. Yeah. Okay, it's odd. Okay, I'm sorry about that. But yeah, now all we need to do is create another button, because we also want to be able to create a new item, right? And we're just going to call this, we're going to add a text right here and say add new item. And every time we click on it, so we use the click. My God, why is this so slow? And we want to, right here, we will want to use the add new item case object, and we're also going to send it to our store. And actually this, let's just add a comma right here. This should just work. Let's see if it actually does something. Not yet. It's just gonna see what happens here. Okay, it's working. It's just taken. I'm not sure why my computer is slow right now. I'm sorry. There we go. Okay. Oh. Okay. So now we have our functioning app. At least I hope it's functioning. And you can see here we can enter an item. And yeah, basically what it does is we have a small thing where we can have a dynamic list of items. I think I'm pretty much out of time right now, so I was going to do some more, but if you want to check out more, basically just come up to me. I have lots and lots to show. I'm just going to return to those slides right now because, yeah. So, conclusions. Reactive programming is just functional programming plus the aspect of time, right? So our streams are asynchronous in nature, and they basically represent values over time. Another thing is we can use this to model very different architectures. I've just shown you the Elm architecture, but there's also different architectures you can check out on the OutWatch project site. Another thing we can do is, what this allows us to is create applications using only pure functions and values. So there's no side effects really going on here. The effects are all at the edges of our program. And functional programming patterns still apply, right? So observables, streams are functors, they are applicatives, they are even monads, even though it's not really useful that they're monads, but they are, and we can use cats and all of these cool things as we like. And the cool thing about the whole thing is we get an extra level abstraction, but we can still maintain flexibility, right? So OutWatch kind of is like a high-level library, but it's also extremely flexible. The only constraint it actually lays onto the user is that he works with observables or streams. So what you actually do with these streams is completely up to you. You can just do whatever the hell you want with it. It's really flexible in that sense. Like I said, you can model very different architectures using OutWatch. And that's it. Thank you very much for listening. You can find more. I'm not sure if you can read this, but at outwatch.github.io. You can check out my Twitter at Luka Jacobowitz and my blog. But yeah, I think we have time for questions. Yeah, so go ahead. Questions?
Just wondering, do you have any experience with what the graphics rendering performance is like? Like if you have a really complicated page or something?
Yeah.
Like you talked about the virtual DOM or the VDOM. Are you actually using a VDOM, or are you manipulating the DOM directly?
No, it's completely based on VDOM. So okay. For DOM operations, it's extremely fast. Actually, I think it's in some cases it's faster than React, because React doesn't know exactly where your changes are, so it's not really isolated. Whereas in OutWatch, because of the observables, because they are bound to a specific component, we only have to we only have to diff that certain subcomponent. Whereas React, by default, diffs the whole VDOM tree of both of the whole application. Yeah, if you're talking about graphics like Canvas, that's currently not supported in OutWatch because it's kind of difficult, because there's no VDOM abstraction for the Canvas. But yeah.
I really just meant the DOM rendering performance and not having to basically give it a whole new DOM, just basically modifying the DOM and then just letting the browser re-render it.
Yeah, no, that's really efficient, at least from what I know. Okay, any more questions? All right, and thank you very much again, and have a great conference.